докладом о квантовых технологиях и сингулярности. Александр Львовский, доктор философии Колумбийского университета, физик-экспериментатор, профессор института Калгари, ну, and so on, so on.
Thank you. So it's of course an honor and a pleasure to be here. Now my talk is titled Quantum Technologies and Singularity, and it's a bit provocative, and I'm going to actually talk much more about quantum technologies than singularity, but I hope to show you which quantum technologies actually have a promise to bring the singularity closer and which have less promise. So that's the outline of the talk. First, I'm going to just give an introduction. Why?
Александр, одну секундочку. То есть, ну все же, разумеется, от Львовского ждут русского языка. Представляете, что бы с вами сделали в 1937 году за выступление на английском?
Ну, это же интернациональная конференция.
И год не 37-й. Well, what about now? Can you hear an interpreting while I'm speaking English? 1, 2, 3, 4. Mary at the cottage door. We can keep going in English, but just a technical speech. Вы не слышите перевода? Так, ну, волшебник Саня. Окей. Значит, вы, well, you know what you have to do while you don't hear any interpreting. You should call волшебник Саня. Yeah, I'm very sorry, Alexander. Yeah, I'll add you extra 3 minutes.
Okay, cool, thanks. So, yes, so first I'll talk about why we come to quantum technologies and why we need them, why it's inevitable, and then I'll introduce a few specific quantum technologies that are going to develop in the near future, and then finally I'll say a few words about the effort here in Russia to develop them. So, I'm sure at this conference, this plot, the Moore's law has been shown, and here I'm showing you Moore's law, but in a somewhat different perspective, the curve not going up, but going down. So here I show not the number of transistors in a machine, but the size of an individual transistor, and you see that this curve is going down exponentially, and quite soon it's expected to reach the size of an individual atom. And then, of course, the tendency will have to somehow stop or change, because obviously, you know, once the transistor becomes less than atom, then there is nothing to make it out of. So something has to happen. And actually, well, we are going to have trouble not even in 2050 or 2030, but sooner than that. Because very soon, we are going to cross a fundamental boundary between the macroscopic world, the world of big things that we live in, and the microscopic world of microscopic objects that's governed by completely different laws, the laws of quantum physics, compared to the macroscopic world that's governed by the laws of classical physics. And that's really a completely different physics there. So it's like you would imagine yourself, you would come to a stadium and discover the ball going through both goals at the same time and behave differently just because the audience is watching. So,
if you can speak a bit too slower.
Okay.
25%.
Okay, I'll try my best. So the point is that when we are crossing this boundary, then all our technologies, all our experience, all our skills that we gained through the last hundreds of years, 100 of years of developing classical computing, classical electronics, will suddenly become useless. And therefore, it's already a good idea to start now developing quantum technologies and preparing ourselves for the quantum age, and well-trained specialists and so on. And furthermore, quantum technologies are not really just going to give us trouble. In fact, they are going to give us a whole range of new opportunity, a whole range of new horizons that are going to change our life in the in the life of the next generation to almost the same extent as semiconducting electronics has changed our life in the past 50 years. And that's what I'm going to talk about. Let first me give you a definition that's like my own definition, not everybody agrees to it. But my definition is that quantum technology is the ability to control quantum systems at the level of their individual components. So let me first talk about the most successful so far quantum technology, namely quantum cryptography. Well, quantum cryptography is an ancient art of sending secret messages through insecure channels, right? So suppose there is sender Alice and receiver Bob, right, who are communicating via a channel, but the channel can be eavesdropped upon by eavesdropper Eve. And, well, sort of so far, cryptography has developed along two main approaches. One approach is actually thousands of years old. That's the approach of so-called one-time pad. It's when Alice and Bob prearrange to share some kind of secret key that is not known to them but not known to anybody else, and then Alice can encode her message using that key, and Bob then decrypts the message using the key, the same key, and of course whoever eavesdrops on the message doesn't have a key and cannot understand the message. This is a perfectly secure approach and also very simple. It existed for thousands of years. The trouble is that prearranging sharing of this random secret information, secret key, is actually difficult, right? It's expensive. You need to send it. Well, nowadays you would send a courier with a briefcase, you know, attached with a handcuff to his hand, full of CDs. It's expensive. So therefore, for most practical purposes, what people use is so-called public key cryptography. That's, well, for example, when you're buying a book on the internet, you're entering your credit card number. And this credit card number is sent to a server in an encrypted way, right? Well, if you think about it, it's quite non-trivial, because your machine and the server previously never had an opportunity to communicate. So they could not agree on a secret key. And the only communication that occurs now is only occurring via insecure channels. And nevertheless, it's possible to encrypt the information. How is it possible? Well, it's quite an ingenious algorithm, and basically it's based on, well, on some mathematical problem that sort of one of the parties invents and then gives to everybody else. And this problem is difficult to solve by means of any modern computer. And because of that, it's difficult to decrypt the message, right? But of course, so this works. That's how most of the modern cryptography is operated. The trouble is that, of course, we don't know that in the future we will not be able to develop some computer, for example, a quantum computer, that will be able to decrypt the message. And therefore, there is no guarantee of security on public key cryptography security. And that's where quantum cryptography comes into play, because it's sort of, the idea is to gain advantages of both these worlds. So how does quantum cryptography work? The idea of quantum cryptography is to encode every bit of information in the quantum state of an individual quantum particle, namely particle of light that's sent via fiber optical channels. And one of the primary postulates of quantum mechanics says that a quantum state of an object cannot be measured without changing it, right? So suppose there is an eavesdropper, right? So suppose there is a fiber optic line between Alice and Bob, and there is an eavesdropper who is trying to, you know, steal those photons and measure their state and steal the message, right? Well, then the eavesdropper will inevitably modify the message, and then the message will never, and then the message will reach the receiver, the Bob, will reach Bob, in a modified way, and then they will immediately, Alice and Bob will immediately be able to see that the message has changed, and then detect the eavesdropper. Here, So that's the basic idea of quantum cryptography, and you see that the security of it is guaranteed by fundamental laws of physics rather than the complexity of a certain mathematical task, and it's inexpensive, right? So they do not have to have communicated previously in order to exchange secret messages. One thing you have to understand about quantum cryptography is that it's not science fiction. It's something that we have today. There are actual companies that, that produce commercial quantum cryptography apparatus, and they actually can be plugged into commercial quantum cryptography, commercial fiber optical networks, and can be used for communication. The trouble nowadays is that quantum cryptography is limited by about, well, a few tens, maybe a couple of hundred kilometers, and there's a lot of research on the way to improve the situation. Actually, I'm involved in some of this research, and there is hope that in a few years we'll resolve this and we'll have quantum communication on a global scale. Another quantum technology that many of you have heard of is quantum computation. And it's kind of controversial, and I would like to address this controversy. Well, first by kind of trying to explain the idea of quantum computation. Well, as you know, in classical standard modern computers, information is encoded in terms of bits, right? And a bit can be in a state of either 0 and 1. Now, in quantum mechanics, basically I'm going to now give you the essence of quantum mechanics in 5 seconds. In quantum mechanics, whenever an object can be in two quantum states, right? For example, an atom can be either the electron in an atom can be either in a ground state or an excited state. So what quantum mechanics basically says is that whenever two states are possible, it's also possible to have a so-called superposition state that is the sum of the states or a difference of the state. So like the famous Schrödinger cat, right? Schrödinger gave this example. The cat can be in a state of being dead or in a state of being alive. And that also means, according to quantum mechanics, that it can also be in a superposition state of being both dead and alive. Now, a Schrödinger cat is quite a complex system, right? So basically what we have in terms of our atoms or in terms of our quantum bits is that we have like multiple atoms in the ground state, a set of atoms in the ground state, and a set of atoms in the excited state. And that's called, this complex superposition state is called an entangled state, in Russian, сплетенное или сцепленное состояние, или перепутанное состояние. And it's this entanglement that gives power to quantum computation. Let me give you an example, sort of a very basic example of how entanglement empowers computation. Let's think of a telephone book. So we have a city of 1 million inhabitants, and well, suppose we have a phone book, so like 10 bytes. Each entry consists of 10 bytes of the name and another 7 bytes of the number. So altogether, we need 17 million bytes, 17 megabytes, to store the information contained in a phone book. That's in a classical computer. But in a quantum computer, what we can do is just use 17 quantum bytes and store the entire information as a quantum superposition of states of these bytes, as shown here, right? So in this way, you have reduced the amount of the amount of data you used by a factor of 1 million. And furthermore, if you want to somehow process this information, for example, if you want to add a prefix to your set of numbers, then you would do it just once. You would not do it one entry by one entry, as in a classical case, but you would actually do it all in parallel. And that's the power of entanglement, that's the power of quantum computing. But, well, there is a lot of bad news about quantum computing. The first bad news is that entanglement, that is this quantum superposition of complex objects, is extremely fragile, right? Every little interaction with the environment will destroy your entanglement. Yeah, and that kind of explains why we do not see Schrödinger cats walking around. Because as soon as you know, this cat interacts with the environment somehow, it will immediately collapse into either the state of being dead or in the state of being alive. And the same reason why it's very difficult to build quantum computers. In fact, today's most complex quantum computer contains only 14 bits. Well, here's a picture. It's like a register consisting of trapped ions. So that's one bad news. The second bad news is that quantum computer is not really too useful. Like, it will never replace this laptop, for example. Why it is so? Again, let me just give you a simple conceptual answer. The real science is much more complicated. But basically, as I said, the quantum computer solves problems in a superposition state. That is, it solves many problems at the same time. That's great. But that also means that the answer will also be in a superposition state, right? And then how would you, but you don't need the answer in a superposition state, you need one particular answer. So you need to somehow be able to extract this answer out of the superposition, and that's not easy. And that's why, in fact, quantum computer is only useful for a very limited class of problems. Moreover, today, there is only one problem that's known for which quantum computer is going to be very useful. But this problem is particularly important, and here it is. That's a problem of prime factorization, a problem that you all have had to solve in your math classes at school, decomposing a large number into prime factors. That problem seems easy for small numbers, but it turns out to be extremely difficult for modern classical computers with large numbers. And while that's, well, it is difficult for classical modern computers, and that's the problem which is the basis of public key cryptography. And as it turns out, quantum computer is able to resolve it quickly, right? So that means that the quantum computer will be able to decipher modern cryptographic codes, or to put it in an almost profane way, it's like whoever first invents a quantum computer will be able to, well, discover all military secrets or get all the money in all the banks, whatever they prefer. And, well, you know that, well, there was a lot said at this conference, that our society is based on information security. Any minor disruption of information security would cause major trouble to the society, right? And that's exactly what the quantum computer can do. So the quantum computer is not a tool of creativity. A quantum computer is a weapon of cybernetic warfare, at least in its modern common view. Let me say a few words about a few other quantum technologies that well, have sort of the ideas that have emerged in the past years. One idea is, well, quantum simulators. And, well, another cornerstone of our today's society is material science, right? The way we are able to develop so quickly is because we constantly invent and develop new materials. Now, in order to develop new materials, what we need is good understanding of solid-state physics, right? That sounds boring, but that's really, really important for information science. And the problem is that right now, we don't really understand solid-state physics. Yeah? Solid state is a very complex quantum object, right? We have a whole bunch of atoms and electrons packed into a tiny little space. And we cannot really model it with a modern computer because it's so complex, and we do not understand it, so basically, right now, material science is more or less about shooting in the dark. And what the idea of quantum simulation is to model the solid state using a quantum system, using another quantum system with known properties. In particular, what people do is they trap atoms cooled down to a temperature near absolute zero, and atoms is a relatively known quantum system, its properties are known, and therefore one can understand solid-state physics by studying those atoms. And well, there's a number of applications. Of course, material science can have many applications. For example, one could eliminate losses in power transmission lines by means of room temperature superconductivity and develop outer strong alloys, which means cheap aircraft, and so on. Another quantum technology, also a modern idea, also stems from Harvard, is, well, quantum sensors. And here's the idea. Well, suppose you have a crystal. Now, a crystal, say diamond crystal, diamond is carbon, right? And suppose in the crystal we have some kind of impurity, say a nitrogen atom, right? Now, what people have learned to do very recently is to control and measure the quantum state of this impurity with an extreme degree of precision. Now, why is it useful? Well, suppose this impurity is in the neighborhood of, say, a neuron, right? Well, the neuron is operating, so it's firing, and it's creating its fields. It's creating fields, and then this field modifies the quantum state of the impurity, right? By measuring the quantum state of the impurity, we can then see what's going on in the neuron. So effectively what we have is a microscope with an extreme degree of precision and extreme accuracy and extreme resolution, right? So what kind of application are we looking at? For example, we can introduce this impurity into a biological cell and study the function of the cell with the resolution of individual cells, or perhaps with even with the resolution of parts of the cell. Or we can understand the function of neural networks, or we can understand even, and even eventually, hopefully, we can reverse engineer the human brain and, well, bring the singularity closer. So, unfortunately, I have very little time left to speak about the Russian Quantum Center, but basically there is an effort going on to develop, and the kind of bold effort, the bold vision that we have is to set up an institution that that would be compatible by its structure, funding, and salaries, and so on, with international research institutions. And of course, the Russian way of organizing science is very different from international, and we are trying to overcome this, so we are trying to sort of make the Russian scientific community a part of the international. And, well, what we have so far, what we've been able to do so far, is bring on board some leading figures of international quantum science. In particular, we have two Nobel laureates here, and they're of course not coming to Russia, but they are going to govern and advise us. And we hope to eventually have a relatively large institute of 100 to 200 scientists that would, also an institute that would become, like, hopefully one of the top 5 international quantum research institutions. So to summarize, quantum technologies I hope to have convinced you that quantum technologies are going to give us a lot of new opportunities. Basically, the revolution in the society that quantum technologies are going to produce is going to be similar to the revolution that semiconductor electronics has created in the society in the past 50 years. Thank you for listening.
Thank you very much, Alexander. Ну, все поняли, что квантовый компьютер можно не покупать. Мы не получили, кстати, ответа, покупать ли квантовый iPhone.